quiet archive record. Tonight, we pass into a world that asks nothing of you. No urgency, no weight, just the quiet unfolding of a story. In October of 2022, the Nobel Prize in Physics went to 3 scientists whose work helped settle a long-running argument about what quantum physics is really saying. Alain Aspect, John Clauser, and Anton Zeilinger built and refined experiments that tested a family of ideas known as Bell's inequalities. These tests were not about tiny technical details. They were about whether nature has a hidden, pre-written script for what particles will do, or whether some outcomes only become real in the act of measurement. Over decades, the experiments became cleaner, faster, and harder to explain away. The result was clear enough that the Nobel Committee could call it a foundation for modern quantum information science. Tonight, we go through the Nobel Prize that was given for proving reality is not real. Imagine you are watching 2 friends play a game with sealed envelopes. Each envelope holds a card, either red or blue. You can open your envelope at any time, and your friend can open theirs at any time, even if they are far away. In an ordinary world, it is natural to think the cards were already decided when the envelopes were sealed. Maybe you just did not know the color yet. The surprise is only in your ignorance. The strange thing about the quantum world is that in many cases, experiments behave as if the card inside the envelope was not decided until the moment you opened it. And even stranger, experiments behave as if your choice of how to look, not just what you see, matters. It is not only that you did not know the answer, it is that the answer was not there in the same way before you asked. That sounds like magic, but it is not presented as magic in physics. It comes from a specific set of predictions. Quantum theory predicts strong correlations between measurements made on 2 particles that were once linked or entangled. These correlations are stronger than what you can get from any model, where each particle carries a complete set of local instructions that decide every possible measurement result in advance. John Bell turned this into a test. He found inequalities, like speed limits for correlations, that every local hidden variable theory must obey. Quantum theory predicts situations that break those speed limits, so the challenge was simple to say and hard to do. Create pairs of entangled particles. Send them to 2 separated measurement stations. At each station, choose a measurement setting. Record the outcomes. Then look at the statistics. If the results violate Bell's inequalities, the data cannot be explained by any theory, where measurement outcomes are determined by local properties carried by the particles alone, with no faster-than-light influence between them. This is where many people jump to the phrase, "Reality is not real." That phrase is sloppy, but it points at something that is genuinely unsettling. If you try to keep the idea that outcomes were always fixed ahead of time, you must give up something else that feels basic. You might have to give up locality, the idea that influences cannot travel faster than light. Or you might have to give up realism, the idea that physical properties exist with definite values, independent of measurement. Or you might take a third route and say the experimenters are not truly free to choose their settings, because their choices are secretly correlated with the particles, a view called superdeterminism. Each option is weird in its own way. Before we get to the Nobel-winning experiments, it helps to be clear about the puzzle Bell was aiming at. In the 1930s, Albert Einstein, Boris Podolsky, and Nathan Rosen wrote a paper that is often called the EPR paper. They argued that quantum mechanics seemed incomplete. Their intuition was that if you can predict the value of a quantity with certainty, without disturbing the system, then that quantity should correspond to an element of physical reality. They described a scenario where two particles interact and then separate. Measure one, and you can instantly predict the result of measuring the other. Einstein disliked the idea that measuring one could instantly affect the other across space. He called that spooky action at a distance. He preferred to believe that the particles carried hidden information that made the outcomes certain all along. For years, that debate had a fog around it because it sounded philosophical. Bell made it testable. He said, in effect, if the world works the way Einstein hoped, then these inequalities must hold. If the world works the way standard quantum mechanics says, then there are experiments where the inequalities will be violated. A useful analogy is to think about two dice that are built in a special way. You roll them far apart, but their results are correlated. If the dice are ordinary objects, you can imagine that the correlation comes from how they were made. Maybe the factory put hidden magnets in them, or maybe each die has a pre-written list of outcomes that it will show for each possible way you might roll it. That would be a hidden variable story. But Bell's result says that for certain quantum correlations, no hidden list that stays local can reproduce the observed pattern if you assume the experimenters are free to choose how to measure. The core of a Bell test is not just to show correlation. Plenty of classical systems show correlation. The core is to show correlation that is too strong in a very particular structured way for any local hidden variable model. To make that precise, we need a simple thought experiment. Suppose there are two observers, often called Alice and Bob. Each has a measurement device with two possible settings, like a switch that can be set to A1 or A2 for Alice, and B1 or B2 for Bob. Each measurement produces one of two results, like +1 or 1. A local hidden variable theory says that the results are determined by some shared hidden variable, call it lambda, created when the particles were together. Alice's result depends on her setting and lambda. Bob's result depends on his setting and lambda. But Alice's result cannot depend on Bob's setting, and Bob's result cannot depend on Alice's setting, because that would require faster than light influence. Bell derived inequalities that constrain the correlations between Alice's and Bob's outcomes across the four combinations of settings. In one common form, the CHSH inequality, the constraint can be written as a bound on a quantity S built from these correlations. Local hidden variable theories must satisfy Thich-Jan Jiakyo 2. Quantum mechanics predicts that for certain entangled states and certain measurement choices, S-huge can be as high as 2.828, which is 2 times the square root of 2. This is not just a small difference, it is a clean gap. If you see S significantly above 2, with good statistics and good experimental controls, you have ruled out a whole class of explanations. The Nobel Prize recognized the path from Bell's paper to experiments that actually closed the escape hatches. Early experiments had loopholes. A loophole is not a flaw in the math. It is a practical gap where a local hidden variable story could still hide. Over time, physicists built experiments that closed these loopholes one by one. One of the earliest landmark experiments was done by John Clauser and Stuart Friedman in 1972. They used entangled photons produced in an atomic cascade. The setup was hard. They had to measure correlations in the polarization of photons. Polarization is like the orientation of a wave's wiggle. A polarizer can be set at different angles, and it will pass some polarization components and block others. When you measure the polarization of a photon, quantum theory says you do not reveal a pre-existing polarization in a simple way. The result depends on the angle you choose to measure. Clauser's experiment found a violation consistent with quantum mechanics. That was a big deal, but it did not end the debate. One reason was the detection loophole. In many photon experiments, you do not detect every photon. Some are lost. If you only count the detected ones, a clever local hidden variable model might exploit the losses. It could claim that the detected subset is biased in a way that fakes a violation. Another issue was the locality loophole. If the measurement settings are not chosen fast enough, or if the stations are not far enough apart, then in principle, a signal traveling at or below the speed of light could coordinate the results. Alain Aspect led a famous series of experiments in the early 1980s that addressed the locality loophole more directly. Aspect's team used entangled photons and introduced fast switching of the measurement settings while the photons were already in flight. The idea was to prevent any slower-than-light signal from telling one station which setting the other station had chosen, in time to adjust the outcome. Aspect's experiments again supported quantum mechanics, but there were still concerns. The switching was faster than before, but still not perfectly random or perfectly isolated, and the detection loophole remained a major issue for photon experiments. Meanwhile, the meaning of Bell violations was being argued in an intense way. Many physicists were practical. They said the math works and the experiments match. Stop worrying about what it means. Others said, no, this is telling us something deep about the structure of the world. At this point, it helps to separate three ideas that get tangled together. First is the idea of realism in a specific sense, that measurement outcomes reveal properties that were already definite. Second is locality, that influences do not travel faster than light. Third is freedom of choice, that the settings chosen by the experimenters are not secretly correlated with the hidden variables of the particles. Bell's theorem says you cannot keep all three at once and still reproduce the predictions of quantum mechanics. The experiments suggest nature behaves like quantum mechanics, so at least one of the three has to go. If you drop realism, you might say the properties are not definite until measurement. That is close to the usual Copenhagen flavor. If you drop locality, you might say there are non-local influences that connect the particles. That is close to the de Broglie-Bohm pilot wave view, where particles have definite positions, but are guided by a wave that can have non-local effects. If you drop freedom of choice, you enter superdeterminism, where everything, including your seemingly free choice of settings, is part of a single prearranged pattern. There is a fourth way that some people mention, which is to deny that the quantum state describes a single world. In the many worlds interpretation, the wave function never collapses. All outcomes happen in different branches. The correlations come from the structure of the universal wave function, not from faster-than-light signals. When people say reality is not real, They often mean that the naive picture of a single classical world with properties that exist whether or not you look is not the right way to think at small scales. But the world is still real in the sense that it has consistent rules. What changes is what we can say existed as a definite fact before certain interactions. To get a feel for this, consider a simple example with polarization. Suppose you have a photon prepared in a state that is polarized at 45 degrees. If you measure it with a polarizer at 45 degrees, you will always get a pass. If you measure it at 0 degrees, you will get a pass half the time. Before you measure, you might be tempted to think the photon has a definite polarization, like an arrow pointing in a direction. But quantum mechanics says the state is not a simple hidden arrow. It is a set of probabilities that depend on the measurement you choose. Entanglement makes this more dramatic. Two photons can be prepared in a state where their polarizations are linked. If Alice measures her photon at one angle and gets a result, Bob's photon will show a correlated result if he measures at the same angle, even if they are far apart. If the results were fixed in advance, you could imagine each photon carries a list of instructions for each angle. But Bell says no local instruction list can match the full pattern for multiple angles. Now we can step through the chain of experiments that led to the Nobel. Start with Clauser. His work in the early 1970s turned Bell's ideas into an actual experimental program. He also helped develop the CHS inequality, which was a form that was easier to test in the lab. The CHSH inequality is one of the most used forms in experiments because it fits naturally with setups where each observer has two settings. Clauser's tests were done with the technology of the time. Photon sources were weaker, detectors were worse, timing electronics were slower, yet the violations were seen. Aspect then improved the tests, especially by focusing on fast switching. His experiments were a major public symbol that the quantum weirdness was not just a math trick. It could be tested. Zeilinger's work, starting in the 1990s and beyond, pushed entanglement experiments into a new era. He and his collaborators learned how to create entangled photons more reliably, manipulate them with optical devices, and distribute them across larger distances. This made entanglement not just a philosophical test, but a resource. A key step was the development of better photon sources, especially using a process called spontaneous parametric downconversion. In simple terms, you shine a laser into a special crystal. Occasionally, one high-energy photon turns into two lower-energy photons that are entangled. This method made it easier to produce entangled photon pairs on demand compared to older atomic cascade methods. With better sources and better detectors, experiments began to close loopholes. One of the big milestones was the so-called loophole-free Bell test, achieved in 2015 by multiple groups using different approaches. These experiments closed both the detection and locality loopholes at the same time in a single setup. One famous approach used entangled electrons or atoms rather than photons, because matter systems can have higher detection efficiency. Another used photons with improved detectors and careful selection. The key point is that by 2015, the community had strong evidence that the Bell violations were not artifacts of imperfect experiments. The Nobel Prize in 2022 was not only about those 2015 experiments. It was about the long arc of work that made them possible, and about how entanglement moved from being a debate topic into being the basis for technologies like quantum cryptography, quantum teleportation, and quantum computing. Quantum cryptography is a good place to bring in a concrete, everyday analogy. Imagine you want to send a secret message to someone. In normal encryption, your security depends on math problems being hard to solve. If someone had a super powerful computer, they might break it. In quantum key distribution, the security can come from physics. If an eavesdropper tries to measure the quantum signals used to create the key, that measurement disturbs the signals in a detectable way. This is another place where the idea that measurement creates reality shows up. In quantum mechanics, you cannot measure a system without affecting it when you measure in the wrong basis. So the act of spying leaves fingerprints. But to be fair, none of this means your everyday macroscopic reality is an illusion. Your table is still there. Your phone is still there. The quantum strangeness shows up in specific conditions, usually when systems are small, well isolated, and measured in carefully chosen ways. So what did the Nobel Prize really say? It said that experiments strongly support the idea that the world cannot be described by local hidden variables. That is a precise claim. It does not say the world is not real. It says the classical idea that properties are definite and local before measurement is not compatible with the observed data, unless you accept other unusual assumptions. Now we can explore the implications you asked for: God, simulation theory, and other facets of life. We have to be careful here, because quantum foundations is a real scientific subject, while claims about God or simulation can slide into speculation. First, implications for God. Many people want quantum mechanics to be proof of something spiritual, like consciousness creating reality. Some popular books claim that human observation is required for the universe to exist. This is not what the physics says. In quantum mechanics, a measurement is not necessarily a human looking. A measurement is any interaction that causes a system to become correlated with a larger system in a way that makes interference between different possibilities effectively disappear. In plain terms, if a photon hits a detector and triggers an electronic signal, that is a measurement. No human has to be present at the moment. So quantum mechanics does not directly suggest that God or human minds are needed to collapse the wave function. Some interpretations do bring in consciousness, but they are not the mainstream approach in physics, and they are not required to match the experimental data. However, if you are thinking philosophically, you might say the experiments force us to rethink what it means for something to be a fact. In classical thinking, facts are there whether or not anyone checks. In quantum thinking, some facts may not be definite until a specific interaction happens. That can raise questions about what exists means, and that can connect to old philosophical and theological questions. But it is not a straight line from Bell tests to God. Second, simulation theory. The idea here is that the universe is like a computer program. Some people think quantum randomness or quantum discreteness hints at computation, like pixels on a screen. Again, the experiments do not prove simulation. They do show that the world is not like a simple local classical machine. But there is an interesting angle. If the universe were a simulation, it might choose not to compute certain details until they are needed, like a video game that does not render parts of the map you cannot see. Some people see a similar flavor in quantum measurement. where outcomes are not definite until measured. The problem is that this is only an analogy. Quantum mechanics is not just lazy rendering. It has specific mathematical rules about probability amplitudes, interference, and entanglement. And the Bell violations show correlations that look like they are coordinated in a way that is hard to imitate with simple local processing. If you wanted to build a simulation that reproduces Bell violations, you would have to include either non-local updates or pre-shared information that is coordinated with future measurement choices, or many worlds, or something like that. In other words, simulation does not remove the weirdness. It just moves the question. Now, other facets of life. One reason the Nobel work matters is that it has practical results. Entanglement is not only a philosophical oddity, it is a tool. Take quantum's teleportation. The name sounds like moving objects instantly, but the real process is about transferring a quantum state from one place to another, using entanglement and a classical communication channel. You do not send matter faster than light. You use an entangled pair as a resource, and then you send two classical bits of information. Once the receiving side gets those bits, it can reconstruct the state. A simple analogy is to imagine you and a friend have two locked boxes that were prepared as a matching pair. You can do a local operation on your box and a special measurement that produces a small amount of classical information. You send that small message to your friend. With the entangled resource and your message, your friend can make their box end up in the same state as the original thing you wanted to send, even though the original is gone. In quantum computing, entanglement allows computations over many possibilities at once, in a way that can speed up certain tasks. But quantum computers are hard to build because entanglement is fragile. Interaction with the environment causes decoherence, which is a process where quantum superpositions effectively turn into classical mixtures. Decoherence is one of the reasons why, in daily life, you do not see cats that are both alive and dead. The environment constantly measures and remeasures everything around you in tiny ways, scattering information. That makes macroscopic superpositions practically impossible to observe. So there is a sense in which reality becomes more classical as systems get larger and more entangled with their environment. But underneath, the quantum rules still apply. Now we should go deeper into the experiments, because you asked for many experiments and a clear chain. One key theme is improving randomness and timing. In Bell tests, if Alice and Bob choose their measurement settings slowly, a signal could travel from one station to the other and coordinate results. To avoid this, experiments use fast random number generators to choose settings at the last moment. Another theme is improving detector efficiency. If you miss too many events, you can open the detection loophole. Modern detectors, like superconducting nanowire single photon detectors, can detect photons with very high efficiency. Another theme is increasing distance. If the stations are far apart, it is easier to ensure that no light speed signal could coordinate them within the time window of the measurements. There have been famous demonstrations across kilometers, and even space-based tests where entanglement is distributed via satellites. A striking example is the 2017 satellite experiment by China's Mikius satellite, where entangled photons were sent to ground stations separated by over 1,000 kilometers. That kind of distance makes the locality constraints extremely strong. But again, the Nobel Committee in 2022 focused on the foundational work that made these things possible, especially the work on entanglement itself. Aspect's work helped show that the correlations persist, even when measurement settings change quickly. Zeilinger's work helped show that entanglement can be created, manipulated, and used as a resource for information tasks. Clause's work helped show that Bell inequalities are not just theory, but testable and violated. To make this more intuitive, it helps to imagine a classical trick and see why it fails. Suppose Alice and Bob agree on a strategy in advance. They will each receive a question, either X or Y. They must answer either +1 or 1. They want their answers to be correlated in a certain way. If they cannot communicate during the game, the best they can do with a pre-shared plan has a limit. That limit matches Bell's inequality. Quantum entanglement lets Alice and Bob do better than any pre-shared classical plan without communicating during the round. That is what the Bell violation means. It is as if they have a stronger kind of shared resource than any classical shared randomness. This is why Bell tests are related to the field called device-independent quantum information. In some protocols, you do not even need to trust what is inside your devices. If you see a Bell violation, you can certify that certain kinds of quantum behavior must be happening, and that can guarantee security or randomness. Now, what are we supposed to think is real in this story? One safe statement is this: the world does not behave like a collection of local objects with properties that are fully defined independent of measurement in a way that can explain all quantum correlations. Something about that classical picture is wrong. If you prefer to keep locality, you may lean toward interpretations where outcomes are not definite until measurement, or where reality is relational, meaning that facts are relative to interactions. If you prefer to keep realism, you may lean toward non-local hidden variable theories, like Bohmian mechanics. If you prefer to keep both realism and locality, you might explore superdeterminism. But then you are saying that what you call free choices are also part of the same hidden pattern. Some people take the many worlds route, where there is no collapse. In that view, the wave function is real, and all outcomes exist in different branches. The Bell correlations come from the structure of entanglement across branches, not from any signal. Notice that none of these options are nothing is real. They are different ways to redraw what you mean by a physical fact. Now let's talk about easy examples and analogies, because this topic can become too abstract. A helpful everyday analogy is to think about asking questions that are not compatible. In daily life, you can measure a book's weight and its color without trouble. In quantum mechanics, there are pairs of questions, like position and momentum, where the act of measuring one affects the possible answers to the other. So it is not that reality is fake. It is that you cannot assume there is a single underlying list of answers to every possible question waiting in the system. The list does not exist in that classical way. Another analogy is to think about a song. Before you play it, the song exists as a set of possibilities stored on a device. When you press play, you get a specific experience in time. That is not perfect because the song is fixed, but it shows how a description can represent potential outcomes, and the actual event is something that happens. In quantum physics, The wave function is like a description of potential outcomes. The measurement is like the event where one outcome becomes the result that is recorded. Now, what about God, again, in a more careful way? Some people argue that if reality is not fully determined, there is room for divine action or free will. Quantum randomness could be seen as openness in the physical world, but randomness is not the same as agency. Random outcomes do not automatically give you meaningful freedom. Others argue that if observation matters, then mind must be fundamental. But again, in physics, observation can be physical interaction, not conscious awareness. So the cautious conclusion is that quantum foundations does not settle theology. It does, however, show that the world is not as simple as classical determinism plus local mechanics. Now, simulation theory again, with a clearer point. If you try to simulate quantum systems on a classical computer, the resource requirements grow quickly because entanglement creates a kind of combinational explosion. This led some people, including Richard Feynman, to argue that to efficiently simulate nature, you need a quantum computer. That suggests that if the universe is a computation, it is at least as powerful as a quantum computation. But that does not tell you whether it is a computation running on something else. And if you imagine the universe as a program, you still have to explain why the program has quantum rules and Bell violations. You have not explained it away. You have renamed it. Now, the implications for other facets of life can include how we think about information and reality. In classical physics, information is often seen as something you can copy freely. You can measure a thing, write down its properties, and copy the record. In quantum physics, there is a no cloning theorem. You cannot make a perfect copy of an unknown quantum state. That is not a technology limit. It is a rule. This rule is connected to the same structure that produces Bell violations. So quantum reality has built-in limits on copying and on certainty. That is a different style of reality than the classical one. As we move forward, we can unpack the major loopholes and why they matter. The detection loophole is about missing events. If you only see some fraction of the pairs, a local model could claim that the hidden variable controls whether a particle gets detected, and that the detected subset is biased toward outcomes that create an apparent violation. The locality loophole is about communication. If the two stations are not truly isolated in the relevant time window, then a classical signal could coordinate them. The freedom of choice loophole is about whether the random setting choices are truly independent of the hidden variables. If not, Bell's inequality derivation can be undermined. In modern experiments, physicists try to close the freedom of choice loophole by using random number generators based on physical processes, sometimes even using cosmic photons from distant stars to choose settings. The idea is to make it extremely unlikely that the hidden variables in the lab could have influenced the choice. This leads to a more general feeling. Bell tests do not just ask about particles, they ask about the structure of causality. If you want to keep a local realist view, you end up with a universe where the choices made by experimenters are correlated with the properties of the particles in a deep way. That is unsettling because it makes the scientific method feel strange. It would mean that any experiment you do could be part of a prearranged pattern that makes it look like quantum mechanics is true. Most physicists do not like that. but it is not logically impossible. Now, it is important to explain why the Nobel Prize phrase, proving reality is not real, is not the official claim. What is proven, in a strong experimental sense, is that local hidden variable theories cannot explain the observed correlations, assuming fair sampling and independent choice of measurement settings. With loophole-free tests, the assumptions are tightened. But there is still room for interpretation. Physics gives you the constraints. Philosophy and interpretation choose which assumption to give up. So a more accurate headline would be, the universe is not compatible with local realism in the naive classical sense. Yet, for a listener, the phrase reality is not real can be a shortcut to the emotional truth. The world is not what it felt like it had to be. From here, we can explore a few big interpretive frames. One frame is Copenhagen. In this view, the wave function is a tool for predicting measurement outcomes, and the act of measurement is a primitive concept. Reality is what is observed, and asked about unobserved properties is not meaningful in the same way. Another frame is many worlds. In this view, the wave function is a real physical object, and it evolves deterministically. The randomness is subjective, from being inside a branch. The correlations in Bell tests come from the fact that the branches are entangled. Another frame is Bohmian mechanics. In this view, particles have definite positions, and a guiding wave has non-local influence. Bell violations are natural because the theory is explicitly non-local. Another frame is relational quantum mechanics. In this view, properties are not absolute. They are relative to an observer or system. Facts are about relations. Each frame tries to keep some part of the classical intuition and drop another. Now, you asked for easy examples. Here is one that helps some people. Think about a pair of gloves in a box. You have one box with a left glove and one box with a right glove. You send one box to a friend far away. When you open your box and see a left glove, you instantly know your friend has the right glove. That is a correlation, but it is not mysterious. The gloves were determined from the start. Quantum entanglement is not like that. If it were like that, it would fit local realism. Bell shows that the correlations in quantum experiments cannot be explained by pre-existing glove-like properties for all possible measurement choices. A closer analogy is to imagine that the boxes do not contain gloves, but contain a device that produces an answer when you ask a question, and the question you ask can be chosen in different ways. If you and your friend can choose different questions, and you see a certain pattern of answers across many trials, quantum mechanics predicts a pattern that no pre-installed classical device can reproduce, unless the devices can talk faster than light, or the questions were secretly coordinated. So the key is that the measurement choice matters. This is why modern Bell tests pay so much attention to the timing of the setting choice. They want the choice to be made after the particles have left the source, so that the particles cannot know in advance which question will be asked, unless you accept superdeterminism. Now we should also talk about why this does not let you send messages faster than light. Even though the correlations are non-local in some sense, quantum mechanics still obeys a no-signaling rule. The outcome at Alice's station looks random to her. She cannot control it to encode a message. Only when Alice and Bob compare their results later do the correlations show up. So you cannot use entanglement as a faster-than-light telephone. It is more like two books that contain matching patterns of random letters, and the pattern only makes sense when you line up the pages and compare. But unlike books, the pattern is not pre-written in a local realist sense. That is the point of Bell. At this stage, we can connect the story to the idea of reality in daily life. In daily life, we use a model where objects have properties, and those properties exist whether or not we look. That model works extremely well because decoherence makes quantum effects average out and become stable. When you bounce light off a table, trillions of photons scatter. The environment gains information about the table's position. The table's quantum state becomes entangled with the environment. In practice, the table is in a stable classical state. So reality at human scale is not fragile, it is robust. What the Nobel-recognized work suggests is that beneath that robust surface, the world is stitched together in a way that does not match our naive classical assumptions. Now we can return to the experiments and add more detail about the improvements. Clauser's early tests used polarizers and photon pairs with limited efficiency. Aspect improved timing and switching. Zeilinger expanded the toolkit of entanglement, including multiphoton entanglement and experiments in quantum teleportation. Zeilinger's group demonstrated quantum teleportation in 1997, which was an important proof of concept. They also demonstrated entanglement swapping, where two particles that never interacted become entangled through joint measurements on their partners. Entanglement swapping is a good example of why naive realism struggles. Imagine you have two entangled pairs. A is entangled with B, and C is entangled with D. B and C meet in the middle and are measured together in a way that projects them into an entangled state. As a result, A and D become entangled, even though they never met. This can be done even if A and D are far apart. This is not magic. It is a consequence of the structure of the quantum state. But it feels like the world is making connections that do not fit a simple classical story. This also has practical use in quantum repeaters, which are devices that could extend quantum communication over long distances by stitching together entanglement links. So the Nobel Prize is about both foundations and applications. Now, you asked for implications for other facets of life. One is how we think about randomness. In classical physics, randomness is often ignorance. If you knew all the details, you could predict. In quantum physics, there is a strong case that randomness is fundamental, at least in the standard view. The results of measurements are not determined in advance. Only the probabilities are. If you accept that, then there is an objective randomness in nature. That kind of randomness can be used to generate random numbers that are not predictable by any classical process. And in some protocols, the presence of Bell violations can certify that the randomness is genuine. This matters for security and for science. Now, one more big concept is contextuality. This is a related idea. It says that the result of a measurement cannot be thought of as revealing a property that exists independent of the measurement context. In a simple sense, the answer depends on the question in a way that cannot be reduced to a hidden list of answers. Bell non-locality is a special case of this kind of contextuality. If you want a plain analogy, think about a word that changes meaning depending on the sentence. The word alone does not have a fixed meaning. The context matters. In quantum mechanics, some measurement outcomes are like that. Now, what does all this do to your sense of meaning or to questions about purpose? This is where we have to be honest. Physics is not built to answer why the universe exists or what it is for. Physics describes patterns, but learning that the universe does not obey naive local realism can still affect how you feel about certainty. It can make you more humble about what you assume is obvious. It can make you see that the world is deeper than simple common sense. And it can remind you that the way you describe reality depends on your tools and on your questions. Still, it does not give a direct answer about God. If you want to connect this to God, you can do it in at least two ways. One is to say that the universe has a deeper order than classical mechanics, and that order might be seen as compatible with the idea of a creator. Another is to say the universe is weird and open, and that leaves room for mystery. But none of that is a proof. Now, to keep things grounded, we can give a timeline. 1935. EPR paper argues quantum mechanics is incomplete. 1964. John Bell derives his theorem and inequalities. 1972. Clauser and Friedman perform an early Bell test with entangled photons. 1981, 1982. Aspect performs experiments with time-varying analyzers to address locality concerns. 1990s, 2000s. Zeilinger and others develop practical entanglement sources, teleportation, entanglement swapping, and multi-photon entanglement. 2015, loophole-free Bell tests are performed, closing major loopholes. 2022, Nobel Prize recognizes the foundational and experimental work. This is the spine of the story. From here, we can slow down and walk through each milestone with more detail and with more analogies. Start again with the EPR, intuition. Einstein's discomfort was not that quantum mechanics was random. He could accept probability as a practical tool. His discomfort was that the theory seemed to allow instantaneous influences across distance. He wanted a theory where systems have properties, and those properties cause outcomes locally. Bell showed that if you try to build such a theory, you hit a wall. What makes Bell's argument powerful is that it does not rely on the details of quantum mechanics. It uses simple assumptions about locality and realism and derives a numerical bound. Then the experiments show that the bound is broken. It is like proving that no matter how clever your plan is, you cannot exceed a certain score in a game, and then watching nature exceed that score. That is why this feels like reality itself is showing you its rules. Now consider how the experiments actually work at a practical level. You need an entangled source. In down conversion, a laser pump hits a nonlinear crystal. Occasionally, the crystal emits two photons, whose polarizations are entangled. These photons go to two stations. Each station has a polarizer or analyzer that can be set to different angles. The photons pass through and hit detectors. The detectors register clicks, and the timing electronics match pairs. Over many runs, you compute correlation functions. In early experiments, the detectors missed many photons. In later experiments, detectors improved. In early experiments, settings were changed slowly or predictably. In later experiments, settings were chosen rapidly and randomly. In early experiments, stations were close. In later experiments, they were far. Each improvement squeezed out an alternative classical explanation. Now you might ask, what if there is a hidden communication that is faster than light, but still does not allow signaling? That is one possibility. Some interpretations accept non-locality as real but constrained. Bohmian mechanics is an example. It has instantaneous influences through the pilot wave, but it still does not allow you to send messages faster than light, because you cannot control the hidden variables, so the no signaling rule can still hold. This is why it is tricky. Nature may be non-local in a deep way, but still respect the practical causal structure of relativity for information transfer. That sounds contradictory, but it is not mathematically inconsistent. It is just not the classical picture. Now let's bring in an analogy about coordination without communication. Imagine two people who each flip a coin in separate rooms. If the coins are ordinary, the results should be independent. If the coins were manufactured as a matched pair in some special way, you could get correlations. Maybe they are actually the same coin cut in half, with matching magnets. But there is still a limit to how strong and structured those correlations can be. If everything is local and the choices of how to test the coins are independent. Bell's inequality is that limit. Quantum entanglement beats it. So the entangled pair is like a resource that is stronger than any classical shared randomness. This is why quantum information science treats entanglement almost like a fuel. Now, you also asked for other facets of life. One facet is how we build trust. In a classical world, you can often trust that systems have definite states, and you can copy and verify them. In a quantum world, some information cannot be copied without disturbance. That leads to new ways of doing security. It also leads to new ways of thinking about what it means to know something. In quantum mechanics, you can have complete knowledge of a state and still only be able to predict probabilities for certain measurements. That is a different kind of knowledge than classical knowledge. It is knowledge of a rule, not knowledge of a pre-existing fact. Now, we have covered the general picture. Next, we can zoom into the phrase, proving reality is not real, and translate it into precise claims. Claim 1. Local hidden variable theories are incompatible with observed Bell violations. Claim 2. Therefore, either locality or realism, in the naive pre-existing value sense, must be abandoned unless you accept superdeterminism or many worlds. Claim 3. The measurement context matters for what can be said to be real. That is the essence. From here, we can explore what each choice feels like. If you abandon realism, you accept that some properties do not have values until measurement. If you abandon locality, you accept that the world has non-local connections. If you accept superdeterminism, you accept that your choices are part of a deeper pattern. If you accept many worlds, you accept that all outcomes happen. Each option has a cost. Now, to keep the story engaging for 2 hours, we can weave in episodes. We can describe the labs, the devices, the practical challenges. We can describe why photon polarization was used. We can describe how random setting choices were generated. We can describe the debates. We can also ground the listener with repeated simple examples like envelopes, gloves, and games. Now we continue deeper into the experiments, starting with clauses. In the Clauser-Friedman experiment, the entangled photons came from excited calcium atoms. The atoms would emit 2 photons in a cascade as they returned to a lower energy state. The polarizations of the 2 photons were correlated. The experimenters placed polarizers at different angles and measured coincidence counts, meaning how often both detectors clicked within a time window. They compared the observed correlations to the predictions of local hidden variable theories and to quantum mechanics. They found a violation of Bell type inequalities. The challenge was that the detectors were inefficient and the sample was limited. But it was enough to raise the stakes. Aspect's experiments improved the design. One of his key innovations was a fast-switching mechanism that changed the polarizer settings while the photons were traveling. He used acousto-optic modulators to switch between settings quickly. The aim was to make it impossible for one photon to learn the measurement setting of the other side through any slower-than-light signal. This addressed the locality loophole more directly. But to be very clear, those experiments still had limitations. Detection efficiency was not high enough to fully close the detection loophole. That is why, for many years, skeptics could still argue that some local explanation might exist. The final tightening came with later experiments, including those that used entangled ions or electrons, where detection was near perfect, and those that used improved photon detectors. Now, Zeilinger's work helped create the infrastructure for these later tests. He worked on producing and manipulating entanglement in flexible ways. He also helped develop the experimental methods for teleportation and entanglement swapping. These methods are now central to quantum networks. A quantum network is like the internet, but with a twist. You distribute entanglement between nodes. You use entanglement to do tasks like secure key distribution or distributed quantum computing. This is where the Nobel work has a future-facing feel. Bell tests started as a question about reality. They became a tool for technology. Now we can turn to the idea of simulation again, but with a better analogy. In a video game, the world is rendered based on what the player can see, but the rules of the world are still consistent. The game does not violate its own physics engine. In quantum mechanics, measurement outcomes are produced according to consistent rules. They are not arbitrary. So if the universe were a simulation, it would be a simulation with strict statistical laws. But again, this does not tell you it is a simulation. It tells you that some outcomes are not fixed until interaction. Now, a final facet is how this affects the concept of determinism. Classical physics, as many people learn it, suggests a clockwork universe. If you know the state now, you can predict the future. Quantum physics breaks that, at least at the level of measurement outcomes. But some interpretations, like many worlds or Bohmian mechanics, restore determinism at a deeper level. So the experiments do not prove that the universe is fundamentally random. They prove that local, realistic, hidden variable models are not enough. Still, for many practical purposes, quantum randomness is real. Now, we can bring the story back to the human meaning. The Nobel Prize is a moment where a deep question became a settled fact. The world is not local and classical in the way Einstein hoped. Yet Einstein was not wrong to ask. The experiments he wanted to be possible became possible. And in a way, that is the beauty. The question was turned into data. From here, we can continue to explore each implication in more detail, with repeated grounding. We can look at how quantum mechanics forces you to choose between comforting pictures. We can look at how it gives you new tools. We can look at how it leaves room for mystery without making claims beyond evidence. And we can keep returning to the simple fact behind the dramatic headline. When you try to explain Bell test data with a local classical story, you fail. Nature refuses to fit that picture, and that refusal is what the Nobel Prize honored. One way to make the Bell story feel less like a math puzzle is to talk about what the experimenters actually control. In a Bell test, you do not get to control the outcomes. The outcomes are random to each side. What you control is the question you ask. For photons, the question is usually an angle. You set your polarizer to, say, 0 degrees, 22.5 degrees, 45 degrees, or 67.5 degrees. Those angles are chosen because they are known to produce strong quantum violations. If the photon carried a simple hidden arrow, you could imagine it would either pass or fail for each angle, as if it had a lookup table. The Bell result says that if the lookup table is local, and if Alice and Bob choose their angles freely, then the best possible average score has a strict limit. Quantum mechanics predicts a higher score. So the whole game is, can you design an experiment where you can trust the score you compute? This is why loopholes matter. Think of a magician doing a card trick. If the audience cannot see the deck clearly, or if the magician can choose which cards to reveal, the magician can fake almost anything. A loophole is like a place where the magician can hide. Closing loopholes is like moving the trick into bright light. For the detection loophole, the hiding place is lost events. For the locality loophole, the hiding place is time. For the freedom of choice loophole, the hiding place is the random choice itself. Now, a modern way to picture the locality loophole is like this. Put Alice and Bob in two buildings far apart. They each have a device that can be set to one of two settings. They each receive a particle and record a result. To close locality, you want the setting choice on Alice's side and the measurement result on Alice's side to happen so quickly that no light speed signal from Bob's setting choice could reach Alice in time to affect the result, and vice versa. This creates what physicists call space-like separation. It means there is no way within relativity for one event to cause the other. So if you still see Bell violations, you cannot explain them by ordinary communication. For the detection loophole, the picture is simpler. If your detector misses most of the photons, you are only looking at a selected subset. A local hidden variable model could say, I will only let the detector click in cases that make the correlations look quantum-like. The rest of the time, I will disappear into the loss channel. So high-efficiency detectors are like a rule that says you must count the full deck of cards, not just the cards that are convenient. In the 2015 loophole-free Bell tests, several groups used different systems. One group used entangled electrons in diamond defects, called nitrogen vacancy centers. Another group used entangled atoms. Others used photons with very efficient detectors and very careful setup. The details differ, but the shared goal was the same: close detection and locality at the same time. The more you close, the less room there is for a classical escape. This matters because the more you close, the more you can treat the result as a fact about the world. It also matters because it turns Bell violations into a tool. If you can reliably produce a Bell violation in a device you do not fully trust, you can use it to certify things. You can certify that two distant devices are using entanglement. You can certify that the output contains real randomness. You can certify security properties in certain protocols. This is a rare case where an argument about the meaning of reality becomes a practical engineering asset. Now, to make the Nobel theory crystal clear, we can state it in one sentence. The Nobel recognized result is that nature violates Bell inequalities, so the world cannot be described by any theory where measurement outcomes are fully determined by local hidden variables under the usual assumptions. That is the scientific claim. Everything else is interpretation. Now we can take your requested topics one at a time, but we will keep the experiment as the anchor. First, proving reality is not real. A better phrase, in plain English, is the world does not have preset local answers to every measurement question. A local hidden variable story is a story of preset local answers. Bell tests say that story fails. So if by reality you mean preset local facts, then that kind of reality is not there. But if by reality you mean there is a consistent world with consistent rules, then reality is very much there. The hard part is that our normal way of talking about facts does not fit neatly. Second, implications for God. There are two honest ways to talk about this. One is the strict science way. Bell tests do not mention God. They do not require minds. They do not show purpose. They show correlations. So in that strict sense, there is no direct implication. The other way is the worldview way. If you grew up with a picture of the world as a local machine with fixed parts, Bell tests remove that comfort. They show that the world is not just gears. Some people feel that opens a door to mystery, but mystery is not proof. A useful analogy is that learning the ocean is deeper than you thought does not prove there are mermaids. It just means your earlier map was too simple. If you already believe in God, you may see quantum strangeness as compatible with a world that is deeper than human instinct. If you do not believe, you can still accept the experiments and treat them as a lesson about limits of classical thinking. Either way, the experiments do not force a conclusion. Third, simulation theory. Simulation talk often uses a video game analogy. In a video game, details can be computed only when needed. In quantum physics, outcomes can be undefined until measurement. This looks similar on the surface. But there is a key difference. In a normal game, the engine can always store a hidden value in memory, even if it does not show it. Bell tests say that if you try to store all the needed hidden values locally, you cannot match the observed correlations. So a simulation that reproduces the results would need something extra. It would need a non-local update rule, or a global data structure that connects distant events, or a prearranged coordination with future choices, or multiple branches. So simulation does not remove the weirdness. It changes the form of it. You can still ask, if this is code, what kind of code allows Bell correlations without allowing faster than light messages? That is not an answer. It is a restatement of the same question. Fourth, other facets of life. One facet is free will. People sometimes think quantum randomness proves free will. It does not. Randomness is not choice. If your decisions were random, that would not feel like freedom. It would feel like noise. Freedom, in the everyday sense, is about reasons and goals. Quantum physics does not give you reasons and goals. It gives you probabilities. Another facet is meaning. Bell tests can change how you think about certainty. You can be certain about the structure of the world, like the Bell inequality limit, while being uncertain about any single outcome. That is a different kind of certainty than a clockwork universe. Another facet is humility. If a result can be true and still feel impossible to visualize, it tells you that human intuition is not the final judge. Now we can build a larger picture by talking about 3 levels of reality. A level 1 is raw experience. You see a detector click. Level 2 is a model. You say the click means a photon had polarization along a certain axis. Level 3 is an interpretation. You decide whether the polarization was a property that existed before measurement. Bell tests lock down level 2. They put strong limits on what level 3 can be. Now, to fill out the chain of experiments more, we can mention that Bell tests have been done in many forms. Photons with polarization, photons with time bin encoding, where the choice is early or late arrival, ions with internal energy states, electrons in solid defects, even macroscopic circuits in superconducting devices, where quantum states are made of many electrons moving together. The exact platform changes, but the logic is the same. Entangle two systems. Measure each system in different ways. Compare correlations. Test Bell's bound. Now, there is another key concept that people miss. Bell tests do not prove that measurement creates reality in a human-centered way. They prove that if you want a local story where outcomes are preset, you fail. If you choose to keep locality, you often end up saying, outcomes are not preset. But that is a choice, an interpretation choice. If you choose to keep preset outcomes, you must allow some form of non-locality. In that case, measurement does not create reality. It reveals it, but reality is tied together across distance in a non-local way. So even the slogan, measurement creates reality, is not forced by the data. The data forces a trade. Now we can put this trade in a simple everyday form. You have three beliefs. Belief 1, outcomes are fixed before measurement. Belief 2, nothing influences anything else faster than light. Belief 3, your choice of what to measure is not secretly arranged with the system. Bell tests say you can keep at most two of these. That is the cleanest way to explain the implication. Now, to keep the story concrete, imagine the experiment as a series of rounds. Round after round, a source emits pairs. A random generator picks settings. Detectors record results. A computer logs a time-stamped record. After thousands or millions of rounds, you compute S. If S is above 2 by many standard deviations, the result is not a fluke. In the best experiments, the violation is large and clean. This is why the Nobel Committee treated it as a foundation, not because it makes headlines, because it is one of the rare cases where you can rule out a big class of intuitive explanations with numbers. Now, to connect back to your title, we can say this. The Nobel Prize was not for saying reality is fake. It was for showing that reality does not behave like a local hidden script. If you try to picture the world as a book where every page is already written locally, Bell tests tell you that the book cannot be written that way. Either pages are not written until you open them, or the book is written with threads that connect distant pages instantly, or the book contains many parallel versions, or the act of opening was always part of the story. That is the menu. And that is why this prize feels like it touches everything, because it is not only about particles, it is about what it means for a thing to be a fact. If you hold on to that idea, the prize becomes easier to place. It sits at the intersection of three things: a deep question in physics foundations, a set of experiments that got steadily more careful, and a new field that treats entanglement as a resource. The headline can sound like a joke or a provocation, but the underlying achievement is serious. The world gave an answer, and the answer was not the comfortable one. In the end, what the Nobel Committee rewarded was patience and clarity. Take a claim that sounds like philosophy, turn it into a number. Build devices that can measure that number. Remove excuses. Repeat until the only remaining argument is about what assumptions you are willing to drop. And then take that weirdness and build something useful from it. Quantum networks, quantum encryption, quantum sensors, quantum computers. All of these trace back to the fact that entanglement is not a metaphor. It is a real feature of nature, with real experimental signatures. So if the question is whether reality is real, the most honest answer is this: reality is real. But it is not locally pre-written in the way we expected. And once you accept that, the Nobel Prize stops sounding like a riddle. It sounds like a report. This was a quiet archive story, where the story ends, sleep begins,